The idea here with telescoping series is to cancel out similar terms and then see what kind of pattern you get out of it, right? So like with this first example, we had 1 minus a half plus a half minus a third. We wrote down the first three terms and we could easily find a pattern, right? So we saw that the net result that we get is 1 minus 1 over n plus 1, right? From there, we wrote the partial sum, s sub n, as the pattern that we just saw, right? 1 minus 1 over n plus 1. And then from there, to determine whether the series converges or not, all we do is just take the limit of the partial sum, right? So we take the limit as n goes to 0. And if we get a finite value, then the series converges, and it converges to that value. Okay. So that's what telescoping series is, right? Set of a series that comes in the form b1 minus b2 plus b2 minus b3 and so on. We did another example on that. Okay, so let's take a look at what else we did here. Right, so geometric series was next. And geometric series is fairly straightforward, right? You just essentially have a series where each of the terms are just multiples of each other, right? They're just multiplied by a common ratio. So a plus r, or a plus a times r, ar squared, and so on. So the goal is to identify what the common ratio is and what the first term is, right? After that, you can just you can use the formula for what the series converges to determine its convergence, right? And that formula is over here. Right, so for geometric series, right, as long as r, the magnitude of the common ratio, is less than 1, right, then the series will converge to the first term divided by 1 minus the common ratio. Okay, so that's the other thing that we did a couple of examples on that. And then what we did was we took a look at, I think we did the right, properties of infinite series and also the divergence test. So divergence test is very straightforward, right? If you take a series and you take the a sub n and you take its limit, right? If that limit goes to 0, it doesn't mean anything, right? It just means your test is inconclusive. But if that limit ends up as a finite number, then you know for certain that the series will diverge, right? So if the limit as n goes to infinity of a sub n is non-zero, then the series diverges, right? And then we looked at an example of this series here, right? The harmonic series. So the harmonic series is a series where, right, it's a special kind of series where we have the limit approach 0, right? However, the series still diverges, right? So limit n goes to 0 and the series diverges. So this shows that just because you take the a sub n and take the limit, if it approaches 0, it doesn't necessarily mean that the series is going to converge, right? And it's kind of counterintuitive because since you're doing a series, right, of a sub n from n equals 1 to infinity, right, and the limit approaches 0, right, it's kind of intuitive to think that after adding so many terms, eventually you're just going to be adding a bunch of zeros, right?
Yeah.
So that's sort of the trick, is you expect this to happen, but that's not actually what happens. That's why the harmonic series diverges. It diverges, it's just that it grows very, very, very slowly, but it keeps on growing forever. right? So those are the main things that we covered last time. So let's take a look at a few examples, a few practice problems. Let me see. Right, and this problem gives us a series of numbers. Right, we have 1 plus 1/4 plus 1/9 plus 1/16. So 1, 2, 3, 4, and then plus 1/25. Okay, so the question asks to find the partial sums S1, S2, S3, S4, and S5. Right, but we're only going to do 2 of them. Right, let's do S2. Right, so we'll say determine S2 and S5. All right, so we only care about the partial sums S2 and S5. And by the way, this series continues forever, right? We don't know exactly what the, well, I guess we do kind of know, but there's a certain pattern in this series, and it continues forever. And our goal is just to figure out what S2 and S5 are. Okay, so once you determine S2 and S5, I want you to also determine the, what's it called? There's a name for it. I think it's called closed form, but I basically want you to write the series as a summation, right? Summation of A sub n. I want you to write it in this form, right? So first, determine S2 and S5. Then, write the series in the form sum from n is equal to 0 to infinity of A sub n, which means you need to determine the A sub n. Right, so keep in mind these partial sums S2, S5, right? Remember what the definition of a partial sum is, right? S sub n means you're adding all the terms up until the nth term. All right, so let's see. Were you able to get S2?
I was trying to figure out like what I was doing wrong to go about it.
Mm-hmm. Remember, you're just adding the terms up until the nth term, right? So this 2 means sum the terms up until the second term.
Okay.
Right? It's a partial sum, right? So you only sum up to the index.
I don't know. I think I'm overcomplicating it because I thought it would be given in the way that we had in the last session, where it's like summation, like the infinity sign, n equals 1, and then like something like the 1 over n minus 1 over n plus 1.
Let me write it this way. Put it as k equals 1, a sub k up until n. Yeah, partial sums are just as they sound. They're just parts of the sum, right? You're not summing the entire thing. So a partial sum just means take the sum of all the values up until the nth term. right? So you're summing. If the partial sum is 2, you're summing only the first 2 terms. If it's 10, you're summing the first 10 terms.
Okay. Just making sure I wasn't like overcomplicating it.
Yeah. Yeah. This one is going to be quick. This one probably is going to take a little bit of time.
Okay. So should series 2 should S2 be 5/4?
Yeah, right? So it's the sum of the first 2 terms.
Yeah. So for the S5, I know I'm taking like the summation of like all 5 terms, but like, is there a quicker way to do it?
Is there? Yes. Yes, there is. Wait. Is there?
Because I was gonna do the, like match the terms. So like,
Yeah. It's
yeah.
like a formula and then just plug it in.
No, not like formula. Like what I did for S2, like I just basically added 1 as a fraction. So
Oh.
4, yeah.
No, you're gonna have to add all of them individually, but there may be a way. I don't know yet, but there may be a way to write a partial sum formula for this. Or wait. Well, not that I know of. For this one, it looks like you might just have to add them one by one.
Okay.
Okay. So S2, you said S2 is 5/4, right?
Yeah.
Cool. So for S5?
I was still kind of like calculating it. I got the S3, which was like 45/36.
Right.
I believe for S4 should be like, at least, I think the denominator might be like 144. Still calculating that. That's why I was trying to like add a quicker way.
Yeah. I know. You mean you're looking for you're looking for like a quick formula you can use, right? Let's see. Let's say the thing is, I don't know, because it's not like a telescopic series where things cancel and then you see some kind of pattern.
Yeah.
Right. It's easy to write the pattern for the series, but for the partial sum, I don't think so.
Okay.
Not that I know of. Maybe there is. Maybe there's some kind of formula I've forgotten. But for now, let's see if we can combine these terms and get something here. So least common denominator between 4 and 9 it should be 36, right?
Yeah.
All right. So we're gonna get 45. 9, 45 plus 4. Okay, so that's 49 over 36, right? So at this point, it's just going to get insane. So you might as well use a calculator. Right. So
would they give me a problem like this in like the class? Because I think they might not let us use calculators. I'm not sure.
Yeah, they won't let you use calculators in the middle of an exam. Okay. Right. So with something like this, I mean, it's kind of just tedious work. I don't think you'll get this kind of problem in an exam. But, well, let me rephrase that. You would, but the calculation would probably be simpler. So you can actually do it quickly.
All right.
Right. Normally, I would prefer not to use a calculator, but obviously because the numbers get really big, we may have to.
Yeah.
All right, so you should get 5269 over 3600. Right. Okay. Now, if this was a geometric series, right, we wouldn't need a calculator.
Yeah.
There's actually a partial sum series for, or a partial sum formula for a geometric series. Okay, now let's take a look at B. So B is not too bad as well. For B, it wants you to write the series in the form of a summation, right? So the idea is to get the sequence representation of these numbers, which means you're just looking for patterns that each term follows, right?
Yeah.
All right. So do you see any pattern we can use?
For the most part, it's well. First, it starts off as like a regular whole number, and then it goes down to 1/4.
Right.
So I guess it could be a pattern of like 1/4 of each number.
Well, if so, then how come we have a 9 here, right? Because 9 is not a multiple of 4.
Yeah. Yeah, it was just the first guess. It's definitely not a percent either. Yeah, it's somewhere in the denominator that they all have a common. So it's like even number, odd number, even number, odd number. Oh wait. Well, they're all divisible, I believe. Yeah. So 4 by 2, 9 by 3, 16 by 4. And then
Good point.
yeah.
No,
So
you brought up a good point there. Now, because you said the 4 is divisible by 2, the 9 is divisible by 3. So what factors make up the 4?
2. Like
2 and 2, right? What about the 9?
3 and 3.
16.
4 and 4, yeah.
Right, you see the pattern. Right, so when numbers multiply each other like that, what's a shorthand way of writing that?
Oh, squares.
Squares, right? These are all perfect squares. Same thing with the 1. It's like a 1 over 1 times 1, right? Okay, so far we've figured out that these are all perfect squares, right? Now, how would we write that as a formula?
I was gonna say maybe 1 to the power of like negative. So like it would be, you would have the fraction, but it would still be
I see what you mean. Like whatever term you're on, you're raising it to the power of negative.
Yeah, like
negative what?
Well, for the first one, it'd be like -1, and so the power, yeah, it'd be the power of -1, and then for the second one, it'd be the power of -2, then -3, 4, 5.
Nah.
Oh wait, no. It's so it'd be like n to the power of like -2.
There you go, right? So we're gonna say a sub n is equal to n to the power of -2 for n greater than or equal to 1, right? Because our series starts off at 1. So when you have 1, it's just 1. When you have 2, it's a 4th, 3, a 9th, and so on and so forth, right? So let's go ahead and put this as a formula. So we're going to say our n equals 1 to infinity, right? And one way of writing n to the -2 is just 1 over n squared. All right, so sum from n equals 1 to infinity of 1 over n squared. So sometimes, with these series, when you're given a list of numbers, it takes a while to figure out what the pattern is, right? And sometimes you might have to be a little bit creative in coming up to an answer. Okay, so that's good. Now let's take a look at some actual series here. And what we're going to do is verify whether those series converge or diverge. Right?
Okay, so for this one was about summation, right?
Mm-hmm.
Okay, so for the beginning, we were just trying to like get the summation for each part. So it's kind of like sequences,
Right.
where instead of having like an n that we replace with like 1, 2, 3, and 4,
Right.
you're just adding them. So like
Yep.
the S2 is like the addition of like A1 and A2.
Right.
S5 is the summation of A1, A2, A3, A4, and A5.
Correct.
Okay.
Yep. Okay.
And
Good.
for writing the series in the form of the thing I was thinking about earlier, you take those and you find the pattern of it and you write it out
Right.
in like a formula, basically.
Correct. Right. So for the second part, you're looking at the same series. You're trying to find a pattern, and then you write that pattern as a formula, right?
Okay.
And then you're just taking the sum, right?
Yeah.
Now, let's see. Let's work on... so for these next problems, right, it's going to be up to you to pretty much determine whether the series converge or diverge, right?
Okay.
So that means that you need to use what we know about series, right? We've talked about telescopic and geometric series, right? And we already know with geometric series, the rules for it to converge. The absolute value of the common ratio needs to be less than 1.
Yeah.
So let's see. Okay, let's see. So, our first problem here. First problem is gonna be, let's see. We're just gonna say verify that the infinite series diverges. Okay, so first problem, we're gonna write the sum from n is equal to 0 to infinity of 5 times 5 over 2 to the power of n. Right, so you gotta verify that it diverges, right? And you gotta state your reasoning. So let's look at this one. For number 2, we have the sum from n equals 0 to infinity of 4 times negative 1.05 to the power of n. For number 3, we're going to do the sum from n is equal to 1 to infinity of 1 divided by n plus 1. Or sorry, that's incorrect. We're going to do n cubed plus 1 divided by n cubed plus 2. Or sorry, n cubed plus n squared. So that's number 3. And then for number 4, we're going to try... So this one is actually an interesting one that you should know, or, you know, it's good for you to know because it'll show up a lot in Calc 2 series. So n is equal to 1 to infinity of n plus 1 factorial divided by 5n factorial. Okay, so I'm just gonna write the techniques that we've learned so far. Right. So for geometric series, well, let's start with we'll do geometric series. Right. These are series of the form sum from n equals 0 to infinity of a times r to the power of n. And we also talked about the divergence test. Right, so these are the methods you need to keep in mind. You're checking to see if you have a geometric series or if the divergence test will give you anything. Right, so that divergence test says that sum from n equals 0 to infinity of a sub n diverges if the limit as n goes to infinity of a sub n is not equal to 0. Right. So none of these have anything to do with the telescopic series, so you don't have to worry about that.
So for the one yesterday where we had to factor it first, was that because we needed to be like in its simplest form before we did anything to solve it?
Yeah. For that one, it was because the original series didn't look like geometric. Maybe if we had written out the first couple of terms, we would have seen the first few terms. We would have seen that it was geometric. But we rewrote it so that it looked obviously like a geometric, and then from there we can determine what the common ratio is, and then from there determine if it converges or diverges.
Okay. So for the first one, it's in, well, I believe for the first two, they're both like in like the formula for the geometric series.
Yep.
So we can easily put the first 5 terms, right, to like see what's going on. I forgot why we did it, but I knew that it was there so we could later get our common first term. No, our common ratio. First term, and then our absolute r. Yeah, our absolute value of r.
Right. So true. We could write down the first few terms to help us determine those quantities. But like you said, it's already written in the form of a geometric series, right? So there's no need to write out the first few terms, right? When it's written in such a way where we can't clearly see if it's geometric or not, that's when we list out the first few terms and then point out what those quantities are, right? The common ratio and the first term. Here, we don't necessarily have to. We could, but we don't have to because, for example, with number 1, we can already see that the common ratio is 5/2, right? Yeah. So straight from there, we can say, okay, I see what the common ratio is. So this is my R. And I see what my first term is, right? That's my A, right? So now that I know A and R, the question then is this geometric series convergent or divergent?
So for the first two, they should both be divergent, with our A being 5 for the first one and our A being 4 for the second one, with both of them being greater than or equal to 1.
Okay. So first one is definitely divergent, right? So what's your reasoning for it being divergent?
Turning 5/2 into the decimal would give me 1.1, and the rule says that anything that's above 1 in terms of like the series or in terms of your R shows that the infinite series is divergent.
Okay, so true, right? But 5/2 is 2.5, I think, right? 5/2 is 2.5.
Yeah.
But the reasoning is correct. So this is divergent because 5/2 is greater than 1. Okay, so let's go for number 2.
So with the same reasoning, 1.5. So our absolute value should turn that into a positive, right?
Right.
Okay. So yeah, 1.05 is greater than / equal to 1. So our series is divergent because of that. And our A is our 4. So the purpose of the A in this stuff is what again?
Well, the A doesn't play any role when it comes to determining the divergence.
Okay.
Right. So 2 is good. Now, what about 3?
For 3, haven't done it yet, but I was gonna say something about the ratio thing, but would that count here? I mean, like the ends are the same.
Do you mean taking the limit? Is that what you mean?
Yeah.
Okay, so yeah, you're on the right track with that. Right. So I see you want to try using the divergence test, basically.
Yeah.
You want to try taking the limit of this A sub n for n goes to infinity. So yeah, go ahead and take that limit. It should be an easy limit to take. And
it should
give
be
you
1.
Your answer. Should be 1, right? Exactly. So we're gonna say limit as n goes to infinity of n power 3 plus 1 over n power 3 plus n squared equals 1, right? Which is not equal to 0, therefore divergent.
So for the ratio test, not test, but like for the ratio rule, if it was n cubed and the denominator was n squared, would I still be able to take the ratio since it's still
no.
Okay.
Because that rule for limits, right? That rule for limits says that it's when you're taking the limit of a rational function, right? So it's just a rule for getting the limit based on whether the numerator is a higher degree polynomial, the denominator is a higher degree polynomial, or whether the numerator and denominator are the same degree, right? So it's 3 guidelines, right? 3 rules. If the numerator is a higher degree, then the limit is infinity. If it's a lower degree, then the limit is 0. And if the numerator and denominator are the same, then you take the ratio of the leading coefficients.
Okay.
Right? So, so that's good for this one. Let me see. Now for number 4. So this is the thing, right? With number 4,
Mm.
you kind of have factorials going on there, right? So n plus 1 factorial over 5n factorial, right? So for number 4, just keep in mind that a factorial just is the product of all numbers, all whole numbers leading up to that number, right? So n plus 1 is a whole number, so if you take the factorial, you're going to get 1 times 2 times 3 until you get times n minus 1 times n times n plus 1, right? Whatever the n value is. So that's your n plus 1 factorial. You're just multiplying all of the numbers before n plus 1 up until n plus 1. Same idea with 5n factorial, right?
Mm.
So you can factor out the 5 as a 1 over 5, but let's look at what n factorial is, right? So again, it's just the product of all of the numbers coming before n up until you get to n minus 1 times n, right? So this is your n factorial. Remember, that's what it is. You're multiplying the values up until you reach that number. Okay?
Okay.
So, since we're dividing these two, right? Obviously, there's an extra 5 here, right? So I'll just put that here. So 5 times all of this. But yeah, since we're dividing these two values, you can see clearly which values cancel out, right?
Yeah. 1, 2, 3.
Right. 1, 2, 3, all the way up until n minus 1, and even the n cancels. So it looks like
5.
Mhm.
5 as well, or is 5 like on the outside of all this?
Yeah, it's on the outside because somewhere in here there's also a 5 that cancels with a 5, right?
Okay.
So all the values cancel except the last term here, the n plus 1.
Hmm.
Right, so that means that, let me put the 5 out here. But anyway, that means that your n plus 1 factorial over 5n factorial can just be written as n plus 1 over 5. Right, so when it comes to factorials, that's how you handle them. And with limits, with series, you're going to be seeing a lot of these factorials. They're going to show up a bunch. So you have to reduce them to something more manageable, right, before you start, determining whether they converge or diverge.
So factorial is just the product of. So I'll only see a factorial in like summations and series.
Yeah, you'll see it probably in other places, but they show up especially a lot in series.
Okay.
Right. It's like you're almost always gonna see them. So that means we can take this series and we can rewrite it in a simpler format like this, right? n plus 1 over 5. Okay, so now you need to determine whether this converges or not.
Okay, that's the sequence way of doing it. Okay. Our A would be 1, right?
Why do you say that?
because I was thinking, like it in a way, the n is like a variable, and so like there'd be like a one in front of it. Like, would there not be?
Mm, are you looking at this as a geometric series?
Yeah.
Does it look like a geometric series?
Not really. I was thinking like maybe like the same rule with like parentheses and there's like a one in front. You could do the same thing. Or like if you're to transform this thing into like a multiple instead of a fraction, I guess the 5 might be the A, but I'm just doing like quick math. But yeah,
Yeah,
right now look like a geometric series, but you can't simplify it more. So you probably have to use the divergence test.
yeah, because I was gonna say the quickest way, like if remember what we said before, if it doesn't look like a geometric series and you're really curious to see if it is or it's not, the quickest way is to list out maybe the first 3 or 4 terms, right?
Okay.
And then you'd be able to tell quickly whether it's a geometric series or not. Because if it is a geometric series, then each term would be a ratio of its previous term, right?
Mm.
Yeah.
Yeah. I was gonna say it was like divergent, but then I realized I was using sequence rules because I would see that it was kind of like getting bigger, the number on the top.
Yeah. Right. So that makes sense because, I mean, if you took this an and you took the limit as n goes to infinity, right? Well, this is just going to go to infinity.
Mm.
Right. So clearly, this diverges. Okay. Good. So, so I think that's good enough practice. Now let's take a look at some tests that you can use, right? Aside from the divergence test, there are a bunch of other tests that you can use to check whether the series converges or diverges.
So, am I gonna need like alternating series or like I think there's one of like Harrison series or
Every single section in this chapter
hmm,
is part of Calc 2.
okay,
Yeah, all the way to Taylor and Maclaurin series.
cool.
Okay, let me see. Okay. So yeah, we're going to talk about 2 very powerful tests. And these are the integral test and P-series. Okay. All right, so let's get into the integral test first. The integral test. All right. So the integral test, the reason it's important because it allows us to sort of change the summation into an integral kind of format and then take the integral instead, right? Because we know how to take integrals, we know how to get antiderivatives, right? So we change the summation into an improper integral, and we know how to check whether an improper integral converges or diverges, right? We take the limit of that integral to infinity, and if it gives us a value, then it's convergent. And if it doesn't, if it gives us like infinity plus or minus infinity, then it diverges, right?
Yeah.
All right, so let's write the integral test down. So it says that if f is positive, continuous, and decreasing, right, for x greater than or equal to 1, and a sub n is equal to f of n, then the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. Right, so this has to do with the fact that, right, this, if you take a look at this f of x, this is just an improper integral, right? And remember, with improper integral, there are two types that we took a look at, right? So there's type 1 and then there's type 2.
Yeah.
Right? So which type? Do you remember which type of integral this one is? Which type of improper integral?
I believe that one was it was like the A. Yeah, so the type 2 was the one that had like A to B, right? And type 1, I believe this is type 1.
Yeah, this is type 1. The type 2 had, it was a definite integral, right, from A to B. And then there's somewhere in between, there's a discontinuity in there, right?
Yeah.
That's the type 2. The type 1 is when you're integrating from one value to infinity or from minus infinity to another value, right?
Yeah.
So this is a type 1 improper integral. So it's almost like you're taking this summation, and instead of a sub n, you're writing it as a function of n. So let's just say, for example, you had, 1 over n squared. That's your a sub n, right? But you're converting it to a function, right? So f of n is now 1 over n squared. So now you're integrating from 1 to infinity of 1 over x squared dx. You see how that works? You're taking that an, you're converting it to a function, and then you're integrating that instead. And if that improper integral converges, then the series also converges. And if the improper integral diverges, well, then the series also diverges. So they either both converge or both diverge. However, you need to satisfy these conditions. It has to be positive, continuous, and decreasing. So let me summarize that down below. All right, so we need f to be positive, right? Let's say f is positive. Right. The next thing is f is continuous. And then the next condition is that f is decreasing. For x greater than or equal to 1. All right, so those are the conditions you need to check for. If you write your f, right, whatever the a sub n is, it needs to be positive, continuous, and decreasing for x greater than or equal to 1. I'll just rewrite that same thing I just wrote as an example. Say, suppose sum from n equals 1 to infinity a sub n say 1 over n squared, where a sub n equals 1 over n squared. Then we can say f of n equals 1 over n squared is positive, continuous, and decreasing. Right, and we know it's decreasing because every next term, right, you're dividing by n squared, right, larger number squared. Right, so just as a quick summary, right, so integral test, right, your f is positive. We're taking f to be a positive, continuous, and decreasing function for x greater than 1, right, and we're writing a sub n as f of n. Then that means the sum of a sub n and the integral of f of x from 1 to infinity either both converge or both diverge. Right? Again, our conditions are that f is positive, continuous, and decreasing. Right? So let's suppose that we have a series, right? 1 over n squared. Right? So your a sub n is equal to 1 over n squared. Now let's define the f sub n to be the same as the a sub n, right? 1 over n squared. So you can see that 1 over n squared is positive, continuous, and decreasing, right? So every term you get a smaller and smaller value, so it's decreasing. Because if you did like 1 over 4, well, 1 over 4 squared is 1 over 16. 1 over 5 squared is 1/25, right?
Yeah.
So this means that we can write this as an integral. We can now say the integral from 1 to infinity of f of x, right? We had f of n here. So f of x dx is equal to the integral from 1 to infinity of 1 over x squared dx.
Oh, we replaced the n with x.
Right.
Okay.
So now you just integrate this from 1 to infinity.
Okay.
Right. So this just goes back to our improper integral of type 1.
Okay.
Right. So this means that we have the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx, which equals the limit as t goes to infinity of negative 1 over x from 1 to t. This is equal to the limit as t goes to infinity of negative 1 over t minus 1 over 1. Okay. And this is equal to the limit. Well, actually, I can just go ahead and take this limit right away, right?
Yeah.
So this is just going to be equal to, well,
Infinity minus 1.
right,
Which
1
is
over
just,
infinity minus 1.
oh, I was saying infinity. Oh, yeah. Okay.
Right?
So that'd be 0 then, right?
Right, so negative 0 minus 1, which is just positive 1. So this
Okay.
converges, right? The integral
Yeah.
converges. Right, so this doesn't mean that the summation converges to 1. That's not what it means. The integral converges to 1, right? But all this tells us is that this summation, right, the summation we started out with over here, converges.
Yeah.
Say therefore, the sum from n equals 1 to infinity of 1 over n squared converges. So I want you to keep in mind, again, it doesn't mean that it converges to 1, right?
Yeah.
I know in the past examples with the geometric series and the partial sums, right, whatever it converges to, that's what the series converges to. But with the integral test, just as the name sounds, it's just a test, right? And the test tells us that this series converges. It doesn't tell us what it converges to, though.
Okay.
In fact, I think this converges to like pi squared over 6, something like that. But yeah, that's how you deal, or that's how you use the integral test. So let me show you like a picture of what's exactly going on here. Image 1. Okay, so this is like a depiction of like what this integral test is doing. Because essentially, when you convert your a sub n to a function f of x, you're converting from a discrete function, right? Because a sub n is discrete. You only evaluate it for n equals 1, 2, 3, etc. But with f of x, it's continuous. So you can evaluate it at x equals half, 0.2, whatever, right? Any value. So that's what the black line represents. Represents the f of x, whereas the rectangles represent the a sub n's. So if you look at this, right? The f of x is decreasing just like the a sub n, right? And what we're doing is we're taking the area underneath the f of x, right? Because of that integral we used. So since the a sub n is bounded by the f of x, right? It's beneath the f of x. That means that if the integral converges, then the a sub n also converges, right?
Yeah.
So it's kind of like a cap. So if the f of x, we take the area underneath, it gives us a finite value, then we know that, yeah, this one also gives us a finite value.
So, the summation. So, what part of it is representing like the summation? Is it supposed to be a sub n right there, or is the whole thing kind of like a sub n?
No, the pink region, that's the area underneath f of x, and this sort of like purplish region, right? The height of the rectangle is the a sub n, right? So here, 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 Right? The height of those rectangles represent the a sub n. And the delta ends are 1, right? So 2 minus 1, 3 minus 1, right? So the area that the a sub n's, the areas of the rectangles that the a sub n's create, right? We know that those areas converge if the f of x, the area underneath the f of x also converges. Right. So you can see here, this is why they've labeled it a sub 2 equals f of 2. A sub 3 equals f of 3. Right, so the integral test is very useful, and it helps you to come to a conclusion for a whole bunch of different series. Right, you just need to make sure that you're meeting these conditions. Okay, so let's take a look at another kind of test called the p-series. Right, so your p-series test, p-series is very easy to use. There's no calculation involved. You just look at it. If it's p-series, you're done, right?
Okay.
All right, so p-series, right? P-series are just series of the form series of the form sum from n is equal to 1 to infinity of 1 over n to the power of p. Right, so this equals 1 plus 1 over 2 to the power of p plus 1 over 3 to the power of p, and so on. Okay. So an interesting thing about the p-series is that for the case when p is equal to 1, you get the harmonic series that we mentioned before. Right, so for p equals 1, we get the harmonic series. Right, so this is the sum from n equals 1 to infinity of 1 over n, which is 1 plus 1 over 2 plus 1 over 3, etc. Okay, so this is the conclusion for the p series. So we'll say that the p series sum from n equals 1 to infinity of 1 over n to the power of p right, so this converges for p greater than 1, right, and diverges for p greater than 0, less than or equal to 1. right? So your P series converges for when P is greater than 1, right? It can be any value greater than 1, 1.1, 1.2, 1.3, then it converges, right? And it diverges for P between 0 and 1.
Oh, so wait, if it equals 1, then it diverges because of
Right.
the okay.
Right, because if it equals 1, we get the harmonic series, which diverges.
Okay.
Right, so even if P was 1/2, your series would diverge.
Okay.
Right, so this means that whenever you have a series of the form 1 over n to a certain power, all you have to do is just check out the power, right? If the power is less than or equal to 1, then it's going to diverge, right? But if it's greater than 1, it's going to converge. So P series is very straightforward. For example, let's say we have the series n is equal to 1 to infinity of 1 over n to the power of 3/2. Right, well, 3/2 is just 1.5, right? Right, so this is divergent. Or sorry, convergent, I mean.
Okay.
So convergent by P series. P equals 1.5, which is greater than 1. All right, so that's it for this section. Right, this is a very quick section. So let's just do an integral test example. And then we'll be done for the day. All right, let's try this one. So, let's see. Okay, so say apply the integral test to the series. Sum from n is equal to 1 to infinity of n over n squared plus 1. Right, so apply the integral test to this series. Okay, so according to the integral test, right, if we define f of n, and our f is, if we define f of x, right? And our f is positive, decreasing, and continuous, then we can apply the integral test, and we can do the improper integral from 1 to infinity. Right, so let's define our f of x. Right, so we're just taking the same a sub n and replacing all the n's with x. Right, so this is in fact positive, continuous, and decreasing for x greater than or equal to 1. Okay, so since it meets our conditions, we can go ahead and integrate it from 1 to infinity. Right, we can integrate it from 1 to infinity. Right, so
and we change it to the limit of, I believe, yeah, t to infinity, and replace the values with t. Oh wait, no, we replace infinity with t, and the x
Right.
values stay the same.
right.
Afterwards, we
dx here. Right, so afterwards we need to integrate this, right?
mhm.
Okay. So, how do we integrate this one?
For that one, I keep thinking of like taking it to infinity. For that one, what am I doing wrong here? Integrating fractions. I don't know. I need a hint. Like I'm blanking.
Yeah, this one we can use u sub, right?
Oh, okay. Yeah.
Right, 'cause
Because
we
every
got-
time we have an interval, we can use sub. Okay. Yeah.
Right.
So for the u sub, we can u sub the denominator, the entire denominator.
Right.
Yeah. Giving us
U
a
sub.
of 2x and a u of x squared plus 1. So 2x dx. Yeah.
Yeah, 2x dx. Right? And then we just need to divide by 2.
Which will give us 1/2.
And now we can substitute everything in. Right, so we can take the limit.
1/2 of x over u with the little line thingy, I believe.
Right, so we can do, let's see, 1 over u times du over 2. Right, we're just going to integrate this and then replace the x back in and then take the limit.
Okay.
Right, so this would become 1/2 natural log of u. Right, and then that means that this would now be the limit as t goes to infinity of 1/2 natural log of x squared plus 1 from 1 to t.
And that, in doing the fundamental theorem, that's a, which is basically the same thing, except you replace x with 1. And on the other side, you're subtracting it with, instead of 1, there's a t.
Right. So you're subtracting the 1 with 1.
Yeah.
So 1 plus 1 gives us 2. So we're taking this limit here. So as t goes into infinity, what happens?
Basically, well, yeah, as it goes to infinity, I believe it goes to 0, basically. So you have 0 plus 1
You sure
minus
this is
your.
natural log here? Right? You're taking natural
Oh,
log of t.
your natural log of infinity, isn't that 1?
No, natural log of 0 is 1.
Oh, okay.
Or sorry, no, my mistake. A natural
Okay.
log of 1 is 0, right? But
Oh,
your natural log function grows, right, as your inputs grow. Right? So natural log function looks like this.
yeah.
Right? So
Okay.
when t is infinity, what happens?
It's going exponentially without it,
No,
like.
it's not growing exponentially. It's growing logarithmically. Right? So it's still growing though.
Yeah.
Right, so you got your t values here, your y values here. Right, so as t gets bigger and bigger, natural log also gets bigger and bigger.
Yeah.
Right, so it goes to infinity. Right, so
That's. Oh, so as t goes to infinity, the whole thing goes to infinity because
yeah,
ln of 2 would be 0, right?
yeah. Ln of 2 would be negligible because this would go to infinity.
Mhm.
So this means that your entire integral is divergent.
Okay.
Right, so since it's divergent, we can say therefore the sum from n is equal to 1 to infinity of n over n squared plus 1. Let me see if I've done this correctly. 2x dx x. Yeah, natural log of. Yep. Let me see. Yeah. So therefore this diverges.
Yeah.
Okay. So that's good for today. So I'm gonna post these up on the board. I'm definitely gonna be assigning homework on all the new material we've covered so far, especially up to the integral test and all that stuff. Those are very important, right? Going into our next few sections here, because we're gonna cover comparisons, alternating series, ratio and root test, all that stuff.
Okay.
It's good to know all of those tests. All right, man. So do you have any questions about anything we covered here?
I guess where sequences and series play. So do sequences and series not play a role in the tests? I mean, like I know there's the stuff with like the series kind of, but like it's the stuff with like how we did sequences where we have like 1, 2, 3 nth terms gonna play in like the integral tests, because like this
Oh,
seems to be back to like integrals, like the fundamental of like integrals and stuff.
yeah. Yeah. No, it's just that we're using the integral as a tool to help us figure out whether our series diverges. Right. So
Okay.
at this point, we're not even doing sequences anymore because the sequences helped us introduce the series, and our focus is on series, and we're using the integral as a tool to help us determine whether our series converge or diverge. Right. So as we go forward, we're gonna have other tests as well. Right. So there's the comparison test, the limit comparison test, the nth root test, at the ratio test. Right. So there are a few more other tests that we can use. The goal is to determine whether our series converges, because then when we get to power series are series that they're series representations of actual functions. For example, if you have a function f of x, you can represent it as an infinite series. And the goal is to determine whether that series converges to that function or not. Right? So these tests help with that. All right, cool. All right, man. So enjoy the rest of your week. And hold on, let me see. Today's Thursday, right?
Yeah, so tomorrow.
Cool. So I'll see you tomorrow.
All right.
All right, man.
See ya.
Have a good one. Bye.
Bye.